Welcome to this video. Today's lesson is on limits. Let's take one. It's the informal, the very first thing you'd learn about limits. We're going to start with just a very brief notion of the concept, do an example. We're going to look at limits by graphs first, and then to be a little more precise, we're going to go using tables of values, a numerical method. There are many other methods we can look at later, but right now that's all we're going to do. Then I'll show you the notation, the formal notation to write it out, and we'll close by doing a second example. So first off, what is a limit? Well, sometimes a function has a value that seems out of place. So at this x value, the real y value is down there, but the graph itself is all up there. So to distinguish between where the function is and where the function's going to, we talk about the going to as the limit. And I said I was going to talk about the notation later, but here's what the notation is. To talk about that limit, we'd say lim as x goes to, say, this is a of f of x, where this is the function y equals f of x. It'll make more sense later when we actually have a real function to talk about, but that's the idea. This is what f of x is close to if x is close to a. Kind of a mysterious, abstract notion. It's the most important sort of central idea of calculus, the idea of getting close to something without actually being there. So let's take a look at an example where it makes a difference. Here's a function. Now, at 1, this function, well, the top is 0, so you might say it's 0, but plug it into your calculator. You're going to get 0 over, but you put it in the bottom, you get 0. 0 over 0 is undefined. The function does not exist at 1. But the function exists everywhere else. Here's a graph of the function. Notice it does something kind of kooky at 2. This is called the vertical asymptote, by the way. But what's important is what's happening at 1. I didn't even draw any kind of funny little thing there. I probably should have. I probably should have opened a little circle there. But the function is so smooth right around there, that there's a natural value the function should have. Now you could zoom in. You could zoom into your calculator and try to find out what that value is. And that would be a graphical approach. The calculator may not even know there's a missing point. It draws dots. And if it can't draw that dot, it just doesn't. And it draws all the other dots, and so your eye sees a connected line. So the calculator can't even tell there's a missing point. But we can, because we plug 1 in, we know. Now how do we do this? How do we do this more numerically? We create a table of values near 1. So here's a table. It's incomplete. What do? You take values near 1. What's close to 1? Well, 0.9 is. What's closer? 0.99. Closer still. Now, being close to 1 doesn't just mean being under 1. So we also have to have things above 1. And I like to put them in increasing order for a reason. And I'll show you the reason in a second, but I'm going to put ones about as far away, but just on top. Now what I'm going to do is plug each of these into this equation here, this formula. It's a little messy, but you can do it. So while you do that, I'll give you a couple of seconds and try them, and then we'll see if we get the same values. Okay, so I'm going to cheat, actually. Well, it's not cheat. I've already calculated them on my calculator, and this is what I get. Minus 0.9091, minus 0.9901, minus 0. It says 999. Here it's minus 1.001, minus 1.01, and minus 1.111. Those are not exactly the same as these, but they're actually pretty similar. And that's coincidence, not plan. Now, how does this help us determine what the limit is? Well, 1 is right in between here. These values are moving, these values are moving. So the limit the function approaches is going to be right in between. So what's right in between there? Well, there's lots of things in between there. But the most logical value is minus 1. So what would we do? We would write out that the limit is minus 1. Or formally, that the limit as x goes towards, where? Goes towards positive 1, of x minus 1 over x squared minus 3x plus 2 is, what was it again? Minus 1. And that's what we're doing today. Now, a quick second example. I've already calculated all the values. What if we have 4 to the x minus 1 over x as x goes to 0? Plug 0 in the top, you get 0. Plug it in the bottom, you get 0. But it doesn't actually matter, even if it has a value, or if it doesn't in this case. The limit has to do with what happens nearby. And here are some values nearby. That's when x is close to 0. Here are values for the function. You can compute them if you want. Right in between there is where 0 is. So if you notice, there's a trend here. There's a trend here. The value of the function is going to be somewhere in between here. Now, the last time, there was a very logical value. It was minus 1. It was exactly in between. Here, not so much. But we can tell it's going to be about 1.38. I'm going to say 386. If you want more decimal places, more precision, what should you do? Have some more values here. This is how you do it. There are some that don't work, but these two work really well. Look for the trends both ways. Until next time.